What's up, students? Hope you're having the best day of your life today. Today, elevator problems. Whenever physics students see the word elevator in a problem, their minds go crazy. Everything is just a mess. I want to explain all of the forces from a very basic level of just one box in an elevator, two boxes stacked, and even in some cases, we're going to see three, and hopefully end some misconceptions and some mistakes, frankly, that students continue to make. So if you want a little bit more advanced, just go ahead. But I think, the brief introduction probably wouldn't hurt too much either. So first, here is a box that's sitting in an elevator. I won't draw the elevator walls and the elevator roof because we don't necessarily need that. We know that this box, because it has a mass, it has a weight, right? So this box has weight. And we show that weight with an F sub G. And that's pretty much standard across the board. This is the force due to gravity, aka the weight. So now we have this floor here. Now this floor supports the box. It keeps the box from being in free fall. A common misconception, students will say it's supporting its weight. Yes and no. It's not always going to be supporting its weight, but it is definitely keeping it from being in free fall. And this force that supports it, we call the normal force. And that is a force that acts perpendicular to the surface and is just shown by F sub N. This is the support force from the floor. So when we look at the grand picture, right, and this is not really a free body diagram because I am still including the floor, but the two forces that act on this object are its weight from gravity and the force of the normal. Now, these are not Newton's third law action-reaction pairs. I did a video on that if you're curious why they are not third law action-reaction pairs. But frankly, it's two forces only on one object. But from here, we can now talk and describe these forces according to the acceleration of the box. Is this box accelerating or is it moving at a constant speed? Let's start very simple. Let's start with a constant speed. So at a constant speed, we know that A equals 0 meters per second squared, just by definition, right? If I'm at a constant speed, I am not changing speed, therefore my acceleration is equal to 0 meters per second squared. A equals sum F net over m, right? That's Newton's second law. Now, if A is equal to 0, that implies that F net is going to be equal to 0 newtons when I'm at a constant speed, when this elevator is moving up at a constant speed or down at a constant speed, or it's not moving at all. So we can look at F net being 0, and then when we go to solve for F net, which is the sum of the forces in a given direction, so the F net in the y direction here is going to be Fg, if I call down positive, plus a minus Fn. And it is the sum of the forces. This is a minus because it's opposite the Fg. So then when I plug in 0 newtons for F net, because this object is not accelerating, I can say 0 newtons is now equal to Fg minus Fn. This is where I can make the statement that Fg equals Fn. And on the basic levels of physics, this is where a lot of students get confused. They just always assume that Fn is equal to Fg. That is not true. Fn can be equal to a lot of things depending on the object's acceleration or the type of surface that we're on. So we always want to make a formula to solve for Fg. So this is very basic. This would be like the force of the floor is equal and supporting the object's weight. That's why sometimes the force of the normal is equal to the weight, but not always. And a case where not always is whether that acceleration is happening. Is acceleration greater than 0? Is it up or is it down? So now let's take a look at when it's not at a constant speed, when it's accelerating. So when we are accelerating up or down, we can now say that F net is not equal to 0 newtons. All right. So Fg does not now equal Fn. The reason that these were equal is because I was able to plug a 0 in over here. I can't do that anymore because F net is no longer equal to 0. And F net is going to be in the direction of the acceleration. And I know that, once again, from A equals F net over m. They're directly related. If F net is positive, then A is positive. If F net is negative, then A is going to be negative. So we can now make the statement if A is upwards, so if this object's accelerating upward, F normal has to be greater than Fg. And this would essentially mean like the elevator motor is pulling the floor with a greater force than the weight of that object. If A is downwards now, we can say the opposite. Fn must be less than Fg. It's this one right here that's important when we move on to boxes that are stacked. And why this is important is think about the extreme case of free fall. Let's say that this elevator wasn't just accelerating down, it was in free fall. Its acceleration was 9.8 meters per second squared. We would say that we feel weightless. And we know that this feel weightless is kind of like hogwash poopycock. Because you could never be weightless if you have a mass, right? Weight is equal to mg. So you can feel or have the presence of feeling weightless, but you're never ever actually going to be weightless. If the floor is accelerating down at free fall and so is the box, the floor would no longer be supporting any of the weight. They'd be falling essentially synchronized as one. So when we're in free fall, we can look at the extreme case where Fn would be equal to 0 newtons. It would not be supporting any of Fg. So while I'm accelerating downwards, the range of force of normal is anywhere from 0 in free fall all the way up to constant speed, the weight of that object. This statement right here is just very, very valuable to like think about in the back of your mind, right? Fn does not need to equal Fg. The most Fn can be in this case is Fg, but it can go all the way down to 0. It's not Fg itself that ever changes, right? M remains constant, G remains constant, even in free fall. So Fg is always going to be there. But just like a rock that falls from a bridge, we drew this like this with no normal force. There could be a normal, but there's not, right? There's nothing supporting this free-falling object. So it's just Fg, and then if we were to draw Fn, it would just be equal to 0 because there's quote-unquote no surface there to help us. So we can really say in this case, like the normal force is really how much of the box's weight does the floor feel? And this varies by A. So Fn, how much of the object's weight does the floor feel? This depends on A, okay? This is going to be like very basic. If you're here in New York State, this is like Regents level. This is pretty much where you can stop. Very rarely are they going to stack boxes on the Regents level or even just your basic high school physics. But if we want to move on to something like AP Physics 1, we're definitely going to have to stack boxes and we're going to have to make better free body diagrams. So let's take a look at two boxes that are stacked on top of one another at different masses inside an elevator. So just for reference, I will draw these boxes over here. Once again, I will not draw the walls and the ceiling of the elevator. That's really unnecessary. I'm going to call this the floor, just an F, just when I do subs so we understand what I'm talking about. This would be box 1, and this would be box 2. I'll tell you there are different masses. It doesn't really matter what their masses are. But what we need to do when we get to the AP level is we really need to be sharp with our free body diagrams and understanding what forces are acting. And with two boxes, a little bit more advanced, and we'll see how important it is to really make good free body diagrams when we get to 3 boxes stacked on top of one another. So what I'm going to do first is I'm going to look at the free body diagram of just box 1. And what this free body diagram is going to tell me are any forces that affect this box. Guys, first and foremost, it has a mass. Draw your weights on every single box. That is always going to be there. So this is going to be Fg sub box 1. All right. The other force that this box feels over here, it feels the weight or a portion of the weight, depending on the acceleration, of box 2. So what I'm going to do is I'm going to draw this, and these are both from the center of mass, but this is a really, really big point, so I want to make it in red maybe, just so, because this is the one major spot where students get a little bit screwed up. This is the force of box 2 on box 1, all right? Guys, this is not Fg2. This force right here, many students think that this is equal. The force that's being applied to box 1 is FG2. That is not the case. If we go back to the extreme case of free fall, if this entire system was in free fall, the floor would not feel box 1, and box 1 would not feel the weight of box 2 because they'd all be falling in a synchronized fashion. So F2 onto 1 is not FG2. That is so important. The other force that this box feels, and once again, these are all from the center of mass, will make the center of mass really, really big, is the force that the floor puts on 1. Now, this is the force of the normal, yes, but forces of normals can go up really and they can go down. So I'm just going to be very, very clear about what that force represents. That's why I drew these subs. These are all the forces that are acting on this box. If we look at the second box, this box has a mass, so it better have a weight. This is equal to FG2, okay? The other force that this box feels is it feels an upward force from box 1 onto box 2. These are the only forces that act. So if I want to draw the F net that's acting on just this one box, right, I would say F net is equal to FG, I'm going to call it down positive, plus the force that 2 puts on 1, minus the force that the floor puts on object 1. This is the F net of this system right here. Now, depending on the acceleration, guys, we can take what we've learned from that first one so I don't have to reiterate. This is going to be equal to 0 if the box is if the elevator is at a constant speed or accelerating, and therefore the force that F1 puts on the floor puts on 1 will be equal to FG1 plus F2 onto 1, but we don't know. But you'll be able to make that assumption and clear that up. This right here is the mistake that students make. If I look at the F net on this system over here, just box 2, F net will be equal to FG2 minus the force that box 1 puts onto 2. So if I knew the accelerations of the boxes, I could then apply them to these individual boxes, right? Because we know that when we have a system, rule number 1, find the acceleration of the system first, and then shrink our system down to find whatever force we're looking for. But let me just look at using these two, let's make an expression for the F net of the system. It's really all of the forces, right? None of these forces would necessarily go away. So I'm just going to rewrite all of the forces that act. We have FG1. We have the force that box 2 puts onto 1. We have the force that the floor puts on object 1. We have the force due to gravity on the second box, and we have a minus force that 1 puts onto 2. Now, I don't know if you guys noticed this, and if you did, good on you. Pat yourself on the back. You're doing really, really good in physics. Right here, this, guys, is a Newton's third law, action-reaction force pair. We have the force that 2 puts onto 1 is equal and opposite to the force that 1 puts onto 2. So these essentially go away. And this cleans up very, very nicely now to FG1 plus FG2 minus the force that the floor puts on 1, which is really just the force of the normal. We call these action-reaction pairs, these contact forces inside the system, we call them internal forces. And just like when we had a box and a box with tension on each side, and it didn't matter what direction the tension was pointing because they were internal, this is essentially going to be the same thing. But what it demonstrates is that F2 to 1 is not FG2. If over here I had plus FG2, that would make 2 FG2s. And when I was trying to lead my kids in the wrong direction in class today, some of them did say, why do we have 2 FG2s? And we didn't have enough time to really get to why that was the case. But this is why that's the case, because it's not FG2. And this is equal to the F net of the system. Right now, if there's an acceleration, now we would write this as A equals FG1 plus FG2 minus F force onto 1 divided by the mass of 1 plus the mass of 2. This is the acceleration of the entire system. And it's worth noting too, and this might be a little bit of a trick for you, This is like, think of this as a person, right? Like you wouldn't detach the head from the body. So we can essentially, if it makes it easier on you and you have to look at a whole picture and not just one of the boxes, think about it as an odd shaped box that just looks like this, right? Wouldn't this just be the force of 1 plus the force of gravity on 2, right? Or we can just write it as M1 plus M2G. And then this would just be the force of the normal. We can make this system really into just one box. It's not that big of a deal if we do that. And we are allowed to do that because the contact that's happening here, as I mentioned, was an internal force equal and opposite to one another that will cancel out when we do math. Now let's get to that third box just so I can stack one more, and then you'll see that it's not much different from this. Then you can go off and, I don't know, stack as many boxes as your little heart desires. I don't care how many boxes you stack. But if you're still watching, please give the video a thumbs up. Share it with some friends. Let them know that this is the dope gravity forces elevator video. All right, let's stack them all. Let's make, my door said this looks like a birthday cake. Let's say we'll make this look like a birthday cake. 1. No, I'll mess with your minds, actually. I'm going to make this one bigger. Suck it. Just like I did before, this will be a sub F. This will be a 1. This will be a 2. And this will be a 3. Let's do a free body diagram. Here is box 1 coming at you. I'm going to go through this a little bit quicker so I don't have to bore the hell out of you. This is FG. Remember, FG is always there. Remember, this is the force, not the weight. This is the force that 2 applies to 1. And this is the force that the floor puts onto box 1. Those are the 3 forces that act, okay? You see, and here's the big difference with having 3. Nothing on this box talks about box 3. There's no talk of box 3. You can't apply a force to something without touching it. The force that 3 is applying to 1 is referenced here. So that's another reason why this is not F2, FG2. This is just the force that 2 puts onto 3, puts onto 1. If I go to this little box here, everything has a weight. So this is FG of 2. It feels the force. So this is the F that 3 puts on 2. And this is the force that 1 puts on 2. And once again, we see, guys, these are action-reaction force pairs. These are going to be internal. The last one, we see it definitely has a mass, so it has a weight, FG3. And this is the force that 2 puts on to 3. These are also action-reaction force pairs. Now, I tend not to cut corners, right? I would just cross these out if you want to. But what I'm going to do is I'm going to do the F nets of the system, of each system, then the total system, just like I did with the 2 boxes stacked, and you'll see exactly how this works. So the F net of this system, we're going to call once again down positive, FG1 plus FG2 onto 1 minus F of the floor onto 1. That's F net. Here, F net equals FG2 plus the force that 3 puts onto 2 minus the force that 1 put back up onto 2. Now, the AP, they like to word things. Just be very, very careful about this onto that, or being like, just be very, very careful with the wording. Draw pictures if you need to. I am a picture type learner myself. FG3 minus F that 2 puts onto 3. Okay, these are all the forces. Now, once again, the box is accelerating. That's just going to change this over here. And it's going to change A. Not that big of a deal. You can handle it. So now when I go for the system, the F net of the system is going to be FG1 plus F2 onto 1 minus F floor onto 1 plus, now I'm over here, FG2 plus F3 onto 2 minus F1 onto 2. Now I'm over here, plus FG3 minus F2 onto 3. Now let's get rid of some action-reaction force pairs and start leveling out some things. This force here, this force that 2 puts onto 1, that's going to be the same that 1 puts onto 2. Awesome sauce. This force that 3 puts onto 2 is going to be the same as the force that 2 puts onto 3. Awesome sauce. Now we can clean that up a little bit and make it look all nice. Because it's nice. Let's go with a nice fluorescent pink for nice. So F net is going to be FG1 plus FG2 plus FG3 minus the force that the floor puts on box 1. And this would be the same if you combined all of these boxes. This is going to be a weird ass shape. Let me see if I can do it. Not drawing a scale. Oh, it looks like an eye. Look at that. That's the same as saying, look, this is the force of M1 plus M2 plus M3 G. That's how we find the weight. And then the normal force that goes back up. If this thing is accelerating upward, we will know that we need to make sure that the force of the normal is probably going to be greater than the forces downward. Simple as that. Now you can just come in and apply A equals FG1 plus FG2 plus FG3 minus FF1 over M1 plus M2 plus M3. For all you math nerds out there, sometimes they write it as G M1 plus M2 plus M3 minus the force of the normal divided by M1 plus M2 plus M3. Don't cancel them out. That does not cancel. But sometimes they write that FG in its form of MG. Guys, I hope that helped. If you have any questions, leave them in the comments. I do like to answer as many questions. I can probably link you to another one. Like I said, subscribe if you want more. Also subscribe if you're taking calc. My wife does all the calc content. Subscribe, like, do all that stuff. Share with a friend. Tell your class that you found the best physics YouTube channel out there. Peace.